Look at Steve's distance to his house. To reach his house, you could say that Steve must travel half the distance, then a fourth of the distance, then an eighth of the distance, and so on. If you can keep dividing infinitely, would this not equal to an infinite amount of distances, as you can keep dividing in half and adding forever? Well, obviously in the real world, Steve would just reach his house. But what is going on here? This entire question was actually a popular paradox in ancient Greece. About 2,400 years ago, in 400 BC, Leucippus and his apprentice Democritus, two Greek philosophers, were developing an idea that happened to provide an answer to the paradox. The paradox itself assumes that you can divide this ground forever, but maybe you can't. Maybe everything can be divided until you reach a particle that can't be divided anymore. They named this particle atomos, which translated to not cuttable in ancient Greek. Even though Leucippus and Democritus were going in the right direction, most people in ancient Greece didn't really believe their theory, since they had no way to prove it. On top of this, Aristotle and Plato, the much more popular philosophers of the era, believed everything was made of just four elements: earth, water, air, and fire. So, while support of Leucippus and Democritus' theory of the atom slowly died out, Aristotle's four-element theory actually became the generally accepted one. In fact, this theory was accepted for the next 2,000 years. The thing is, humans don't actually need to know what's going on at atomic level to know how to make stuff happen. Humans had known how to create fires by striking two rocks together for millennia. They knew that heating certain rocks could create metals. They knew that combining certain substances would create medicine, and they knew all of this without knowing why it happened. I'm telling you this because, even though for the next 2,000 years, people still believed in Aristotle's mistaken theory, they were still able to make a lot of advancements in chemical reactions, despite not knowing why they actually happened. They were able to make detailed instructions and specific instruments that allowed them to measure exactly which substances transformed into others. So, how was Aristotle's theory finally disproven? And how did Leucippus and Democritus' idea come back to light? For that, we have to fast forward all the way to the 1600s. Meet Robert Boyle, an Irish chemist who highly disliked the four-element theory. You see, Boyle argued that the four-element theory did not actually explain chemical reactions. If everything was made from the same four elements, then it should be theoretically possible to turn any substance into any other. This wasn't really what was happening with chemical reactions though. Instead, it was more clear that two or more substances had to interact to create a chemical reaction. Or, a substance could break down into different substances, which couldn't be broken down anymore. Boyle proposed that pure substances like these were the true elements, not earth, air, water, and fire. And some of the pure substances were reappearing within other substances. So Boyle thought it was actually these elements that made up everything. It's just different mixtures of elements that create different substances. The thing is, Boyle didn't know how many elements there were, but he did redefine what an element was for future scientists to discover, and he helped bring an end to Aristotle's mistaken theory. Over the next 100 years, many different elements would be discovered. But, as you might have noticed, while Boyle did deal a major blow to Aristotle's theory, the original theory of the atom hadn't been brought back. Here's where we meet John Dalton, an English chemist from the 1800s. As I said, scientists had gotten good at describing how to make chemical reactions. Dalton was studying some of these instructions when he noticed something intriguing. At the time, scientists knew three compounds with nitrogen and oxygen in it. Look at this table with all three compounds. Specifically, focus on the weight of the compounds. Between the same element, the weight can only increase in multiples. Nitrogen can only be 14 or 28. Oxygen can only be 16, 32, or 48. But why? Why can't you just have something in the middle? Maybe it's because the weight represents the absolute smallest particles. Just think about it. If there are really small particles that make up each element, then maybe compounds are just combinations of this particle many, many times over. That is why the weights of the elements can only be in multiples. As the particle is added, 2 times as many particles of the same element are in each molecule, which means 2 times as much of the element is in the entire compound. Dalton realized that his theory had been proposed before, so he brought back Leucippus and Democritus' idea, naming this small particle the atom. Nice, Dalton brought back the atom. He actually gave some experimental reasoning for it too. Dalton even made a model. He really believed that the atom was just a simple ball, the absolute simplest, indivisible particle. Dalton didn't think that any smaller pieces made up the atom itself, but Dalton would be wrong. But before we continue, you've got to understand a little bit about charges. Although this is a subject for another video, here's the basics. If you've ever rubbed a balloon on your hair, you've experienced electromagnetic charge. People assumed that this was because when you rub certain things together, they are picking up what they called a charge. They also noted that after picking up a charge, objects would either attract or repel, so they assumed there must be two states of this charge. They named these two states positive charge and negative charge. Things that were charged in the same way repelled each other, and objects with different charges attracted. This knowledge was then used to make a battery, and for now, all you need to know is that chemical reactions happen inside the battery to create a positively charged end and a negatively charged end. Now, people didn't really know what was going on with these charges. However, scientists had discovered that if you put two pieces of metal inside a glass tube, poke a hole in one of them, connect each side to one side of a battery, and really crank up that battery, a beam of energy would shoot out from the negatively charged metal, through the positively charged metal, and out the other end. This was called the cathode ray tube experiment. Scientists suspected that this beam could further explain electromagnetic charges. Also, for some reason, putting elements like helium gas between oppositely charged metals would make the element inside positively charged, in a process called ionization. These positively charged elements could be bent by charged plates. Elements with heavier atoms bent less, while elements with lighter atoms bent more. By comparing how different elements behaved, scientists were able to further work out the relative mass and charge of different atoms. Anyways, it's 1897, and a man by the name of J.J. Thomson wondered if these experiments had anything to do with Dalton's atom. After recreating this cathode ray experiment, he placed a positively charged and a negatively charged plate around the beam. The beam curved towards the positively charged plate, meaning the beam was made of negatively charged particles, as opposite charges attract. This beam was coming straight out of the metal, plus the particles were somehow lighter than atoms. Remember that scientists were able to work out the weight of different atoms by bending them in the ionization experiment, yet the particles in the cathode ray were bending far more than even the lightest atoms. Whatever these particles were, they had to be much lighter than any known atom. So Thomson made a conclusion. If this beam is coming out of the metal, and the particles that make up this beam are lighter than an atom, then these small negatively charged particles must be part of the atom. He named these particles electrons. Thomson then proposed the plum pudding model, where these electrons are scattered around in a big positively charged bubble. This revealed what was truly happening during ionization. The electrons moving from one charged metal to the other collide with the electrons from the helium atoms. These collisions knock electrons off the helium atoms completely, leaving them with less negatively charged electrons, which gives them an overall positive charge. Of course, the atomic model was still not right. It would be proved wrong again, this time through radiation. Here's the basics. In the late 1800s, it was discovered that certain metals like uranium give off a constant visible energy for some reason. Even when they're sitting still, these metals give off enough energy to make certain materials glow. So, scientists decided to see if this energy could be separated by charge. Sure enough, they separated the radiation into positively charged alpha particles, negatively charged beta particles, and neutral gamma rays. Enter Ernest Rutherford, a New Zealand chemist and physicist in late 1800s England. He decided to fire the positively charged alpha particles that were separated from radiation at a sheet of gold. If Thomson's model of the atom was correct, the electrons would be too light to stop the alpha particles, and the positive bubble would be too spread out to repel the positively charged alpha particles. He set up a metal circle around the piece of gold foil to track where the alpha particles ended up after hitting the piece of gold foil. At first, Rutherford's idea was correct. Almost every alpha particle shot straight through and ended up back here. Almost. About 1 in 8,000 alpha particles would bounce straight off the gold foil and head in all sorts of crazy directions. Rutherford reasoned that the only way this was possible was if something massive and compact was within the gold atoms. This mystery thing was probably positively charged, which is why it repelled the positive alpha particles so greatly. Plus, this positively charged thing must have been concentrated in the atom, as only a small percentage of the alpha particles were actually hitting it. So, Rutherford constructed a new model of the atom, with a positively charged particle in the middle, which he named the nucleus, and the electrons circling around it. He thought that some alpha particles were hitting this nucleus and recoiling off of it in different ways. He proposed that the alpha particles were actually shooting through the gold atoms because most of the atom was empty space. Rutherford's new model also explained why the electrons were scattered throughout. They were simply attracted to and circled the positively charged nucleus in the center. There was now a new model of the atom. But after this discovery, Rutherford continued studying the nuclei of different elements. Scientists had already found ways to knock electrons off atoms, allowing them to measure the positive charge of the nucleus. Weirdly enough, some elements were much more positively charged than others. Some had twice the charge of hydrogen, others had 6 times the charge of hydrogen. This suggested that the nucleus was not made of one singular positively charged particle. Instead, it seemed to contain multiple units of positive charge. Rutherford thought that maybe these units were actually individual particles, which come together to make up the entire nucleus. He named these particles protons. Having a nuclear charge of 1 meant there was 1 proton in the nucleus. Having a nuclear charge of 2 meant there were 2 protons, and so on. This model was widely accepted as a new atomic model. But there was just one problem with it: the electrons. But let's pause that real quick because there's some extra science you need to know. Let's talk about light. We'll go deeper in a later video, but here it is. You see, light is just a form of energy. If a specific range of this energy hits the human eye, our eye can pick it up as different colors. Different colors just correspond to different amounts of energy. For example, red has the lowest amount of energy, while violet has the highest amount of energy. Also, you can separate the colors coming from a light source by shooting the light through a prism. But let's talk about ionization one more time. You see, remember that cranking up the voltage on the batteries would knock electrons off atoms and make them positively charged overall. However, scientists also noticed that if you cranked down the energy, the collisions weren't energetic enough to completely knock electrons off the atom. Instead, the gas inside the tube would often start glowing in a separate process called excitation. Scientists wanted to know what colors made up this glow, so they pointed it at a prism and noted the colors that came out of it. They actually realized that each element has a different constant color identity, and every element has a different one. But what does this have to do with the atom? Well, let's unpause. You see, the problem with Rutherford's model had to do with the energy of the electrons. According to the real-world physics of the time, electrons should be emitting energy as they orbit the nucleus. According to Rutherford's model, electrons could orbit anywhere around the nucleus. However, as electrons lost energy, they would no longer be able to maintain their orbit and would spiral inward until they eventually crashed into the nucleus. This meant the atom from Rutherford's model was unstable. But obviously, atoms are stable in the real world, so Rutherford's atom just couldn't be true. But here's where we unite electron energy and the colors different elements shoot out during excitation. And for that, we have a certain Danish physicist to thank, namely Niels Bohr, who was working to connect these two concepts. He proposed an idea. Maybe, Each atom only has certain energy levels that an electron can be in. The further away the energy, the more energy it takes to be in. In excitation, the electrons are not hit fast enough to completely be blown off the atom, but maybe they get enough energy to move up energy levels. Then, as electrons jump back to energy levels that require less energy, they give off the rest of the energy as light, which we can measure with color. The jump from one energy level to another is the difference of energy that's given off. So it's not the energy levels themselves, but the difference between them that causes each element to give off certain colors, which, remember, are just measures of energy. Different spacing between energy levels is what causes different elements to give off different colors. Bohr's idea appeared to explain why electrons did not collapse into the nucleus as well, and why each element gave off a different set of colors. With this, Bohr produced a new model of the atom, with his energy levels included. This atom was the closest so far to the real one, but to finally finish it, we need to check in with one more British man, specifically a physicist named James Chadwick. You see, the ionization experiment revealed something wasn't lining up between the charge of the atom and the weight of it. Hydrogen has a single proton and weighs 1 unit of atomic mass. So surely, the proton weighs 1 unit of atomic mass. After all, electrons are way too small to account for barely any of the weight of an atom, and close to all of the weight is stored in the nucleus itself. However, there was a problem. Helium has 2 protons, yet it weighs 4 units of atomic mass. If protons account for nearly all of an atom's mass, where is this extra weight coming from? One day, James Chadwick was probing around by shooting the alpha particles from earlier at a sheet of beryllium. He noted that strange radiation was coming out the other side of the beryllium sheet. This radiation, however, had no charge, as it didn't react to charged plates. So, Chadwick decided to put a piece of hydrogen-rich wax in front of it. This time, however, protons came shooting out the wax. This was weird for several reasons. First, whatever was coming out of the beryllium couldn't be an electron or a proton, as it had no charge. Yet somehow, it was powerful enough to knock protons out of the wax. This suggested that the radiation wasn't just energy, but a stream of previously unknown particles. These particles had no charge, but they had to be about as massive as protons. Chadwick proposed that there's actually neutrally charged particles inside of the nucleus of an atom. These particles were being knocked out of the beryllium by the alpha particles and then slamming into the protons of the wax. Chadwick named this particle the neutron, adding it to the model of the atom. The neutron also explained the missing weight from the helium atom. So Chadwick added the neutron to a model of the atom and finally completed the atomic model. This is how we get to the model that's recognized and taught in classrooms across the world. Finally, after thousands of years and the work of many thinkers more than were mentioned in this video, our understanding of the atom is finally complete. Right? Well, there's still quantum physics, where scientists realized the path of electrons was much more unpredictable than we thought. And if you haven't noticed, protons in the nucleus don't repel each other despite being positively charged, which uncovered the idea of nuclear energy, the idea that there is a greater force at play between these protons and electromagnetic charge. But both of these topics are going to have to wait for a later video.